Is the video on?
Yeah.
Oh, it is?
Yeah.
Okay. Look at this.
They can't see where you're pointing.
Yeah, so let them see. Okay. Final exam review time. Semester 1, Unit 1, Unit 2, Unit 3, Unit 4. Let's go. So, under Unit 1, we want to make sure that we're going over a few things. So, what I've put on the board are some things that I think we need to kind of refocus on and go from there. Okay, I listened to you guys' suggestions. People were talking to me one-on-one, and I think these are the things that we need to discuss, which is kind of funny when you put like an entire semester of learning on one board, but this is kind of what we've been doing. If you hear any pauses, I'm just writing timestamps on the video. This is going to be a little concise because this is like the 4th or 5th time I've tried to do this tonight, so I'm tired. This is the last shot. Let's go from here. Shout out to my absolutely beautiful camera girl for helping us out. Say hi to the people.
Hello.
Hello. Do you have any wisdom to impart to them?
Do good things.
Do good things. Okay. So first and foremost, chemistry. Chemistry is not only about elements. Okay, that is a misconception. That is not something that we want to have. Chemistry is a study of matter and how it interacts with other matter. Essentially, its changes and its properties. So I just thought it would be fitting to start with that. Obviously here, this is the periodic table, and it has 17 rows, which we call periods, and 18 groups, or columns. Okay, so again, kind of go from there. Not something that we need to worry about too much, but just to let you know that it's kind of the periodic table. We immediately started talking about physical and chemical changes, and again, Monday, which is tomorrow, is going to be the vocab day. We're going to go through everything that we need to know on the final, and we'll just kind of go from there. I just missed a timestamp already. I'm already doing great. Physical change is a change where it's the same material, so it's still the same thing. A physical change is when it's going to be something new.
Chemical.
Something new. So for example, if you burn paper, paper is a sugar, okay? It's kind of just like a glucose, starchy kind of thing. And in this case, if you burn it, it's going to become carbon or just ash. So that is a different material. And again, we did a lab on that, so I just thought I'd go over that really quickly. So just 2 examples with paper, more examples of physical and chemical changes. Could be about maybe physical changes like, mixing something together. Phase changes are in here, so like melting, boiling, things like that. Because again, water is still water. Chemical change, chemical reactions, anything that goes from reactants to products, something new, it's going to be that. Again, signs of a chemical change we've talked about as well. Completely moving along, we also started talking about theory versus law. This is some stuff that's been a while, so I just wanted to make sure that we're aware of it. Theories are, again, really, really, really good hypotheses. Like everything is lined up. I like to compare these to be about 95% accurate. And then laws are 100% accurate. So for example, the law of conservation of mass, you cannot create or destroy matter. If I wanted to have this pen vanish, not possible. And you guys have heard me talk about smoothie vision is my X-Men superpower, also not possible. So just to kind of talk about those two. King Henry died unexpectedly drinking chocolate milk. That one is going to absolutely be under the metric conversions. Again, what we need to talk about is every single step you take this way, you are going to be multiplying by 10. And every single time you go this way, you're going to be dividing by 10. And that is because this end is small. And this end is big. Kilo, hecto, deca, units, which we'll talk about in a little bit. Deci, centi, milli. And again, the base units are, you guessed it, grams, meters, liters for length. Oops. Aha. First mistake. For mass, my apologies, length, and volume. Part of my handwriting is, you guys know it's a little bit small. So that's just kind of a review of that. Next up, scientific notation. When you have a really small number, again, you must put the decimal point in between the first two non-zero numbers. So for example, I wouldn't be starting between this 1 and 2 or this 2 and 1. It needs to be the first two. So this one is going to be 1.1 times 10 to the -1, -2, and -3 power. And this one's going to be 1.301 times 10 to the +1, 2, 3, 4, 5, and 6 power. So again, this way we're going to have a positive exponent. This way we have a negative exponent. And then just to finish off Unit 1, talking about the states of matter. This is going to come down to, of course, solids, liquids, and gases. So with solids, liquids, and gases, again, please remember solids, super compact, super organized. Liquids, a little more spread out. Gases, super spread out. This is a much bigger topic moving forward for second semester. So just wanted to allude to that right now. Key thing is, if you have a volume, let's say it's here, this can be 10 milliliters. And if you pour it into a very thin dish, it only might fill there, but it's still going to be 10 milliliters, okay? So liquids, they can change their shape, but have a different same volume. So this is just something to think about. Solids, you can't mess with them too much, and gases do what they want. These are all over the place. So that is the end of Unit 1. Going on to Unit 2. Unit 2 is when we started to get a little bit more serious, specifically talking about the atom. So the atom, as you can tell, and can you zoom in, can you see the positives? Or should I highlight those? Can you see them?
Just barely.
Okay. I'm going to just highlight these in black. Does that help a little bit?
Better.
Okay, awesome. Protons and neutrons are in the center. So that is called the nucleus. Ooh, I'm switching back to this for handwriting. Not good, is it?
Mm-mm.
Wow. Again, the nucleus is the center of the atom, and that is where the protons and neutrons are, and the electrons are in what we call the electron cloud orbitals. And we can kind of go from there. As we already know too, electrons, very small, very tiny. Mass is 0. The other two masses are 1. And if you don't know the charge of these by now, YOLO. Again, isotopes have the same protons. Neutrons change. And then going through that a little bit. Sorry, I am forgetting to do timestamps, but I'm going to be very close. Ions, these are going to have the same protons, and then the electrons change. And we will get to that when we discuss these in just a little bit. Moving right along, talking about something that I think you guys all enjoyed, the alpha, beta, and gamma decay. Again, with these, alpha particles are 4-2, same as a helium nucleus. Beta is 0 minus 1. Gamma is 0, 0. And again, just like these are going to be breaking apart. So we are going to subtract to get there. So, you don't know this. 235 minus 4.
231.
Correct. 92 minus 2.
90.
90 is correct. And what's element 90? Say thorium.
Thorium.
Thorium is correct. And that's how you do them. 235 minus 0.
235.
Minus 0.
235.
92 minus negative 1 is?
93.
93 for the PhD. Ooh! Element 93. Say Neptunium.
Neptunium.
Neptunium. And there you go. Okay. Please keep in mind that these are breaking apart. Okay, so these are both fissions. Okay. Fission is when you break apart. Fusion is when you come together. So just kind of keep that in mind, because you want to make sure that you are good with that, or else that might be a little bit of an issue. And then to finish off kind of the little bit of the vocab here, atomic number is going to be the number of protons, and the atomic mass is the protons plus the number of neutrons. And again, if you could zoom back up here, that's because these are the only two that weigh anything. So just weigh these. That's it. Cool. Continuing right along with atomic notation, which I apologize for the timestamps. I just want to make sure that I'm getting it all for you guys. With this is the atomic notation. The top number is the mass. The bottom is a number. This is the charge. And because of that, we're actually able to figure out the proton, neutrons, and electrons from this. So if that's the atomic number, and the atomic number is the number of protons, how many protons is this?
What?
So if the atomic number is the number of protons, and this bottom number is the number, what's the number of protons?
92.
92. If you want to find the number of neutrons, all you need to do is subtract these two numbers, and this will always tell you the number of neutrons, which is your boy. Okay, so 235 minus 92 is 126. No, 123? No. $133. And then the electrons come from the charge. So if you have positive 2, we've talked about this a lot. So look over here really quick, okay? These lose electrons because they are positive. We have discussed this in great detail. Anions are negative because they gain electrons. So this would have to be 90 electrons. Very nice. Very, very nice. And then the last little thing to pick up from this unit, which was a little bit quick, is metals, nonmetals. Again, underneath, again, minus hydrogen, this whole area that I'm shading, okay, these are metals. Okay, this section in the middle-ish, okay, these are the semi-metals. And the area that is blue plus hydrogen, these are the nonmetals. So just to kind of keep that in mind. And that, ladies and gentlemen, is Unit 2. Going right along to Unit 3, we definitely need to talk about all of the groups of the periodic table. So as you can zoom in on here, I've already color-coded these. These you do not need to worry about, okay? Big ol' X, essentially. And what it comes down to is these are the alkali metals. Just for speed, you know I don't have enough space, and my handwriting, as you can tell, is not good right now, so we'll go like that. Blue is alkali earth metals. Green, as you all know, transition metals. Halogens are purple. and the noble gases, which are stable. What are they?
Stable.
So these are very, very good. Something else to talk about absolutely in here is valence electrons. Now, valence electrons, as you know, are the outside electrons. So if you actually could go back to this picture, this one right here, this is the valence electron in this lithium atom. So in this case, we would say there is only one valence electron. When doing the valence electrons, I'm going to stick with this orange, okay? It's 1, 2, I don't know about any of these. That's why we talked about it's an elephant's graveyard. We must never go there, Simba. It's a scary place, okay? Over here, we get into a 3 category, a 4, a 5, a 6, halogen 7, and noble gases are 8. And because they are stable, that is called the octet rule. All right, which is a very, very large governing thing, this entire unit. Again, going back down to valence electrons and cations and anions. Cations lose electrons and are positive because of that. Anions are negative because you gain electrons. Essentially, if I give you a negative thing, you're negative. That's kind of how those work. Transitioning to electron configurations and orbital diagrams. With the orbital diagrams, let's actually, maybe talk about those first. And again, I apologize. I'm just trying to write myself some notes. If you have these set of arrows, again, we talked a little bit about the Drake rule, starting from the bottom. Now we here. Okay, I hope this doesn't get demonetized. Now, you have to fill opposite arrows before working your way up. That's the Pauli rule. And then you don't want to be a creeper. You have to go to, actually you're at a restaurant. This is not you, this is a random person. Would you rather sit in an area by yourself or with the creepy stranger?
By myself.
By yourself. Someone else comes in. Are they going to sit with the creeper stranger, you, or by themselves?
By themselves.
Now someone else comes in, there's only that many seats. Guess what they have to do?
Sit by me.
They have to sit by you. Okay? So you have to go through all of the orbitals and double up once you can. Now talking about the electron configurations, we are going to discuss this. You are allowed to use your S, P, D, and F chart on it with the electron configurations. Electron configurations come up from example, this is 1s2, 2s2, 2p4, that is carbon's electron configuration. And then noble gas electron configuration is using the noble gas before it. So the noble gas before carbon is helium, and you would just go from there. So I'll let you zoom in on this just in case. And again, let me know if there's any issues with that. That's all I really want to say about that. You guys did a really nice job with electron configurations. I don't really feel I need to give it extra time. Now, what we do need extra time, focus on these, please. This is the thing that you guys need. Okay, so if there's anything you guys need to remember, it's the periodic table trends, which is the thing that got the most people. 3 trends. Atomic radius, which is the size of the atom. Ionization energy, which is the amount of energy needed to lose an electron. And electronegativity is the ability to gain an electron. Again, as you know in class, I use a shield to kind of represent ionization energy and a sword for electronegativity. It's the attack. Going through these, okay, going down, and again, going to the right is how we're going to talk about these. As you go down, just like Russian dolls, there are more shells. So these atoms get bigger. Okay? Going across, because there are more protons, which mean more pull, these get smaller. Now again, I am exaggerating these a little bit, as you can tell. I'm doing the third row just as an example. Okay, so over here, these are smaller. Fluorine is the smallest. And francium is the biggest. Okay, you guys might remember I had this huge red beach ball, huge for francium, and then fluorine was that tiny little ball magnet I had. It wasn't even close. And this is the most important one. So if you could go back to this one. Okay, I'm putting a bunch of stars around this. This one's the most important because you can easily talk about the other ones. Now, with ionization energy is the defense. So, question for you, okay? Is it easier for you to protect your wallet if it's in your pocket or on a table 30 feet away from you?
In your pocket.
In your pocket, okay? Because you're close to it. If you are close to your electrons, if you are small, these have a very high ionization energy.
Can you use a different color?
Did you see the blue on that or no?
That one that's okay. Yeah.
Is that blue? Is that better?
Yeah.
Okay, thank you. These have a very high ionization energy, and these would have a very low ionization energy. Because again, if you're big, you can't defend yourself. And if you're very small, you can. So again, asking a beautiful camera woman again, if you had your wallet in your pocket, could you protect it?
Yes.
If it's 30 feet away from you on a table, could I just take your wallet if I wanted to?
Probably.
Probably, because it's 30 feet away from you and there's nothing you can do to stop me. That's how that works. And the same line of thought works with electronegativity. Can you see that or no?
Not
Okay.
very well.
Okay.
That's better.
Okay. And the same line of thinking here happens here. If you are big atom, okay? Big atom. It's going to be hard for you to take something, okay? If you wanted to take, if you wanted to take this marker from me right now, my wife, you guys watching the video, could any of you take this marker from my hand right now?
Maybe.
That's right. You can't. See? I'm like Dora. I answer my own questions. Too far away. So literally, try to reach for this. Can you get it?
No.
Can you get this marker?
No.
You're too far away from it, right? But if you have a small radius and I put the marker within your reach, now you can take it, right? I had a very low ionization energy. You had a very low electronegativity. And while we're doing this, check this out. This is a high ionization energy. Go ahead and try to take this marker from me. Try again. That's a high ionization energy. Okay? So that's how that works out. And ladies and gentlemen, that is the end of Unit 3. Going on to Unit 4. Okay? Unit 4 is the last unit that we kind of covered, talking about valence electrons and bonding really quickly. What we have here is valence electrons. So when you're doing the dots, are my dots big enough?
Yes.
Okay. You have to go in a circle. Again, I'm just adding on. You already went over the valence electrons. Again, once you have to pair up, that's when you get the electron pairs. And I know I'm going to be a little cramped on space. Thank you for bearing with me. And again, I know some of you are way faster at this and you can do it quickly. That's fine. I'm just going nice and slow in a circle. And again, going right back. Follow this orange marker. Are you following me, camera guy?
Camera woman.
Did you get the reference I just made?
No.
The slap chop guy.
Oh.
Are you following me, camera guy? It's about to get serious. Even my wife doesn't laugh at my jokes. See what I have to deal with? I got you guys not doing it. How about this? If anybody can remember, tell you what, if any of you come to me and write R2D2 on a piece of paper, I'll give you an extra credit point. Just to see who's paying attention. All right, moving on. So, going from here with these electrons, they're going to go around here, and this is going to help lead you to your Lewis structures. With the Lewis structures, right, the center atom is always the first thing except hydrogen. So if you have SCl2, which we've used as an example quite a bit in the class, sulfur is the center, and it's going to bond to chlorine. And that's going to be our structure. So again, this is the center. The only time it's not the center is H, because H is only one dot. It's too basic. It can't be the center if it's basic. So coming from here, we can use our VSEPR chart, okay? And this is like the 3D stuff. And what we can do is, we know the domain of this. So my wife knows math, but she doesn't necessarily maybe know this. S is the center. How many bonds are attached to the center?
2?
Do you see these double dots?
Yes.
These double dots are called electron pairs. And they count as being on the center. So how many sets of double dots do you see?
2.
So 2 bonds, 2 electron pairs, add those up.
4.
This is the domain 4, okay? And we know specifically that this is a 2 to 2, which means it is bent, and it has 109.5 degree bond angles, okay? You might see, if you're with Mr. Nenya's class, I believe your table says 107 degrees, that's close enough. Essentially, it's saying the same thing. You are allowed to use your VSEPR chart. Lewis structures were recent, so I'm not going into any more detail than that. Just wanted to let you know you are allowed to use that VSEPR chart. It has this part on there. You need to do this. You are given that, okay? And that kind of goes from there. The next big thing to talk about is, and again, I'm doing the time right now, ionic and covalent bonding. Big thing, covalence, share. Share what? Electrons. Ionics take. Take what? Electrons, okay? So because of that, we have a plus 1.7 electronegativity difference, and here, obviously you know what the two parts of covalent are, but we'll kind of talk about that in a little bit. But again, big thing with ionic, okay, and this is where the lab comes in. These are going to be crystals. They're going to be able to be crushed. Solubility, yes. Conductivity, yes. And they're going to do nothing or melt in heat. Covalence, okay, with the lab. Powders, burn. Texture and structure are kind of all over the place. They don't dissolve, they don't conduct, okay? So keep in mind with those lab, with those properties. And then going on to the second to last thing, polar versus nonpolar. With these, polar is unequal. Nonpolar is equal. And again, this is really going to help out, okay? This is literally 50-50. And this is anything else. Okay? Because again, this is going to be, okay, between 0 and 0.4 electronegativity difference, and this is going to be between 0.4 and that 1.7 that we mentioned before, okay? And that's going to be able to tell. Again, we need to be very careful with this idea, okay? So please keep that in mind. Polarity in general. Maria, is this a symmetric shape if S is the center? Can you fold it on both?